Okay, so we continue from this point. So let me just quickly remind you what we did. So we recalled what a we didn't recall. We defined what a configuration is for a deterministic finite automaton. This was like one state followed by a word, basically. So it describes which state your machine is in and what is the input that is left on the tape. But anyways, we will recall this as we go on. So how we ended the last lectures were that we introduced this language here. Maybe I can actually zoom this in here. So this language here, L prime, which is, so you can think of, so you have alphabet is just bunch of ones. So only thing your computer can read is just ones. Well, computer, whatever. So your DFA can read, your alphabet is bunch of ones. And now your language consists of ones to the power 7 times I plus 25j, when I and j are natural numbers, including 0. So this language basically contains multiples of 7s, multiples of 25s, and their combinations somehow. So it contains 32 ones, for example, because if you take I equals 1, j equals 1, you get 32, but it doesn't contain 21. Well, it does contain 21. It doesn't contain 31 ones. Right? Because you cannot write it as a multiple of 7 plus something times 25. Okay, so what? So now, obviously, this language is regular because you can write it as just, we know that just 7 ones is regular because it's concatenation of 7 ones. Then 25 ones is also regular. This is what it's written here. And you just take their union, so 7 ones, 25 ones, and then take the star, so all possible concatenations of 7 ones and 25 ones, of course, give you exactly this. So it's clearly regular because you can write it as union and a star. However, the question is, can we build a DFA that exactly accepts this language and nothing else? And the spoiler last time was that we indeed can do this. And the lemma that we're going to prove in next couple lectures is that regular languages, by definition, these are the languages that can be written as the union, star, right, whatever. So with the definition you know, so I'm not going to repeat. So regular languages are exactly the language accepted by finite automata. What this means that if you have a regular language given by a regular expression like this, then there exists a finite automaton, M, namely, such that this finite automata exactly accepts this language, and vice versa, meaning that if you have a finite automaton, if you draw a finite automata and it accepts some strings, those strings constitute a regular language. So we have to prove both sides. First, whatever you take, so you can start wherever you like, but we'll start this. So we'll start with a general DFA, so deterministic finite automaton, and we're going to prove first that the language that it accepts can be written as union stars and the bars. So we prove this direction first, from right to left. Now we're doing this, but we're also going to do it the other way around. That if it's regular, we're going to construct a DFA that accepts it. But now, first, we're doing exactly what you said. So if you have a deterministic finite automata, general DFA, the strings that it accepts, it's actually, those strings are regular. So yeah, it says lemma 2, but it's just one side of this. It's this arrow from right to left. It's if M is a finite automaton, then language that this automaton accepts is regular. This is what I want to prove. So how do I do this? Right? This is a nice trick that is sometimes used. The way I do it, by the way, maybe I can get the laser pointer. Yeah. So the way I do this is I start with a machine. So the general machine. So what does the DFA consist of? DFA consists of set of states, an alphabet that it accepts, and transition functions that tell you from which state and which alphabet letter where do you go with an arrow like this if you're drawing it. Then you have a start state and you have a bunch of accepting states. If you have something like this, it's a completely general machine. The first observation that I make here, so I start with the machine and I want to prove that the strings that this thing accepts is regular. So I have to write it as unions and cleany stars and bars somehow. But so first I start, so my first observation is that this is a DFA. So one of the requirements is that this Z here, maybe let's enlarge it like this. So this Z here is finite. So these are just Z1, Z2, Z3, whatever, but it has to be finite. It ends somewhere. So I just give this states just names as natural numbers. So I rename the states, whatever their names are, like Z2, Z3, Z4. I just name them 1, 2, 3, 4, 5 up to n. Doesn't change anything. The same machine is written. I just gave, however I wanted, I just gave the names 1, 2, 3, 4, 5, 6, and up to n. It has to have the end one. So it has n states. It's finite, right? So I just rename it from 1 to n. And this is what it means. WLOG means without loss of generality. Oh, yeah, it's written out here. That means that this was a completely general machine. You rename the state, it's still a general machine, but it just has the name. You can always do this. Okay, so I renamed my states are now 1, 2, 3, 4, 5, 6, 7, 8, up to n, however many states this thing has. And now, pay close attention. So I introduce this set. This set is called Rijk. So I is a natural number, J is a natural number, K is also a natural number, right? So what is Rijk? The set Rijk is all words that if I start at state I and I read this word, so I start with W and I read the word, right? So imagine you have a machine drawn. I forgot my stylus today, so I'll try to use my finger. Hold on. Somehow. Here. So here. So imagine you have a machine like this. Yeah, you have a machine like this. Maybe it goes like this. I don't know, like this. Some machine, right? So it's a huge DFA, whatever. So what is this set Ri? Let's say 4, 5, I don't know, 7. So what is this R4, 5, 7? This will consist of all strings or words or however you like, that when you start at state 4, recall I renamed my states with numbers, right? So all my states are numbers, right? So I start at 4, I read this word, let's say I read 1, 2, let's look at like 1, 2, 3, then I go like this, I don't know, and I finish here, and let's say this is 5. So I start at 4, I finish at 5, and all the states in between that I had to pass were less than equal to 7. So, for example, if I had 8 here, this is not allowed. Then this word is not in this R. However, if instead of 8, I had maybe 6 here, and 1 here, and then 2 here, and then 3 here. So if all the states in between, all these blue states that I drew with my finger, so all these blue states were less or equal to 7, and I started at 4, and I finished at 5 when I read the whole word, then this word will be inside 4, 5, 7. Exactly. So let's read mathematics. Exactly that. So these are all words. When you start a computation, basically you follow what we define strictly what computation is, but it's exactly what you're doing when you're following the DFA. In state I, with the word W, this is a configuration when you're in state I in word W, you go to the next state, so you're following it. So you end up in state J, whatever is written here, and your word is empty now, so you read the whole word. Then all configurations between I, W, and J, epsilon, have states less or equal to K. Okay, why do I want this? Okay, why would I want? Now imagine I'm able to prove that this is a regular language. This is just a set of words, right? This is a language, right? Every set of words constitutes a language. Imagine I proved that this thing here is regular. Then what? Then this doesn't work. Oh, here. Now let's go to completely to end. So then, what is the language that my machine accepts? It's all those words, look what's written here, that have start with the start state, end in the final state, and all the states they pass in between are less or equal to n. So if your words start at the start state, and at the final state, so there may be many final states. So I'm taking a union over all finite states, but this once without the union, this one single set is one concrete final state, and this consists of all words that start at zs, this is a number, end at za, and in between every state is less or equal to n. But less or equal to n means it can be anything because there are only n states. Okay, so yes, so I only have to show that each R is regular. By regular, it means that I have to show it again, so it's you can start with a single set, so single letter, take unions, concatenations, and stars, and you have to get the whole thing. Then it's regular. Okay, let's unzoom this again, and so now what I have to prove, basically, is that here, let's zoom in here. So I have to prove that each Rijk is regular, and then it finishes my proof, because if instead of I take the start state, instead of j I take the end states, and for k I take n, and I take the union over all n states, I will get the language that is accepted. Okay, so how do I prove that each Rijk is regular? Remember what Rijk is. It's a little confusing. It's all those words that start in state I, end in state j, and all the states that you pass in between are less or equal to k. Okay, if you get what I'm saying, if you get the definition of Rijk, my question is, what is Rij0? So look, let's say it in words. Rij0 is all the words or all the strings that when you start in state I and read this word and finish in state j, all the states that you passed in between are less or equal to 0. Look, all states start with 1 to n. There is no state named 0. So there is... Როგორ? ხო, ერთი ვარიანტი ეგ არის. So let's look at that. Let's say I equals j. This is what this one says. If I equals j, then I read nothing, or it might be that this kind of thing is happening. The loop is happening, right? Maybe I equals j and I read one letter, a, let's say, or 0 or 1, and I went back. Then this letter will take you from I back to I without passing any other state. So this also works. So if I equals j, either you're reading nothing, as you said, or you're just reading a single letter. Which letter? Such that delta IA equals to I. So in Rij0, either consists of a single letter, in case I equals j, either it's just a single letter or it's an empty set. But the other option is that you directly go from I to j. If they're not equal, the whole point is that if you're looking at Rij0, there cannot be any state in between, because state will have a number and it will be bigger than 0. So Rij0 only consists of single letters or nothing. ხო, მარტო შუებს. The შუები არ უნდა იყოს რა. There cannot be, if you put 0 here, you cannot have anything in the middle. If you have nothing in the middle, either it's just one step, or you're looping, or you're reading nothing. So either Rij0 is just one letter, a single letter that brings you back. Actually, there can be many letters that bring you back somehow. It can be 0 also does this, and 1 also does this, but it's a bunch of single letters, or it's nothing. In any case, we know that this is regular. It consists of single letters, or it consists of epsilon. These things are regular. So so let's write it down. So let's try to draw this. So the situation is like this. So you have a state with number I, and you have a state with number j. So I and j are natural numbers, right? And now what I'm claiming that what is Rij0? This consists of all strings that take you from I to j, but when they take you from I to j, all the things they pass in between are less or equal to 0. So there has less. So if there is a state here, and it has number k, and let's say there is a string that takes you from I to j, like this, then k has to be less or equal to 0 for this word. Let's say this is w1, w2. For w1, w2 to belong here, then k has to be less or equal to 0. Very clever. Because all the states are numbered from 1 to n, this cannot happen. So the only possibility for you is to go like this, directly, without any states. Then, it's just one letter. So it's, let's say my alphabet is B, just for simplicity. So it's just 0 and 1. Then this is either 0 or maybe 1 also goes here. So your thing consists of 0 and 1 in this case. So it cannot have things like this. This is what I'm saying. It cannot have longer string. It just has one letter. But it can also happen that I equals j. So it might be that it's the same state, I equals j, and then you can do something like this also. And you can do something like read nothing. So you can do something like epsilon in this case. Because if it's the same state, you read nothing and you stay there. So this is basically what we're doing. So if Rij0 it's just a collection of one letters or collection of one letters and epsilon. So it's always regular. So now I'm going to do induction on k. So I know that for k equals 0, Rijk is regular. Now I want to prove it that if I know that it's regular for k up to k, I have to prove that it's regular to k for k plus 1. Which actually is a mind bend. Now, how do I prove this? By the way, let's look at this philosophically. What I want to prove, look, what is the philosophy, right? I start with a DFA and I want to prove that the language it accepts is regular. I know that regular language, to define a regular language, I need a union, I need a star, and I need a concatenation. Can it be that I can prove that the language is regular? Let's say I'm given M and I want to prove that the language is regular without using one of those operations. Let me ask you a question in Georgia another way. Point. This is just an intuition that I wanted to give you. But okay. So now I know that Rj0 is regular, and I assume by induction step that Ij, k minus 1, k minus 2, k minus 3, they're all regular, and I want to prove that Ijk is regular. So now here is the you have to flex your brain now. The way I will write, first let me tell you what I will do. Rijk, I want to prove that this thing is regular. If I can write it as Rijk minus 1, this by induction assumption is regular. right? I assumed k minus 1 is zero. If this is equal to, let's say you believe me that this equality holds, then this is regular, then the union, nothing, I can do this. This is also regular because there's k minus 1. This is also regular because there's k minus 1 and there's a concatenation here, star, no problem, and this is also regular. So, ხო ეგ არის induction hypothesis-ი. ნოლზე დავამტკიცე, ხა k minus 1-ზე ვუშვებ, რომ სწორია და ეხა k-ზე მინდა ვაჩვენო. Look, this is just a set of words. Rij0 is actually a language. It's a set of words, set of strings. I know that Rij0 is always, this is a set and it's always regular because it's just single letters and empty set. Now I'm assuming by induction that Rijk minus 1 is always regular no matter what I write for I, j, and k minus 1. What you're really doing is you're starting, so you know for 0, then you prove for 1 using this, then for 2, for 3, and you will get for each ijk. The same way induction proceeds, but by induction hypothesis, I assume that this is regular, this is regular, this is regular, this is regular, and I'm claiming that Rijk can be written this way. If I convince you that it can be written this way, then you tell me, okay, then this is regular because it's union, concatenation, and a star of regular languages. ხო, ეხლა რატო არის ეს სწორი ვაფშე? მოდი ჯერ let me try to explain it. Okay, so what is written on the left side? The left side contains all strings that when you start in I and end with j, in the middle you pass only those states that are less or equal to k. What can the strings be? Now let's look at the first guy here. It may be, so here's the drawing, by the way, which is a very good drawing. It's hard, once you understand it, it's a very good drawing. So you start in I, you end in j, and all the states you passed are less or equal to k. What happens that if all the strings when you start at I and end with j never hit k somehow, they only pass through k minus 1. All the strings are also here, right? So let's continue. So this here is drawn here, as I mentioned, right? So this is I, by the way, and this is j. So you start with I, you get to j, and all the states in between are less than k minus 1. Of course, if the string is here, it's also here, because if the string passes from I to j without ever hitting k, and it's only using up to k minus 1 states, it's also in this set here. Okay, what else is there? Okay, this is somehow understandable. All the other paths somehow from I to j have to pass through k. So these are the ones that start from I, go to j without ever hitting k, but all the others hit k. So let's imagine I started I and I'm going like this and I hit k. Right? I think I have it written somewhere. Oh, these writings do not show up here, or what? Have it right? Oh, here. The writings do not show up in the full screen view, so let's look at it like this. So it says, first time we met k somehow. So you're going like this and you hit k first, right? Then you also continue going like this, and maybe you hit k again. What happened? You got this. Okay. So you start with I, you hit k, and so you started with I, you ended in k without ever, so if it's the first time you met k, all the states before were less than k minus 1. So you started in I, you came to k, all the states on your road somehow were less than k minus 1. Then, this is the last time you met k. You started at k, then, so you went to k, then you started at k, you traveled again, hit the K many different times. So you went from K to K with passing only the states that are less than K minus 1 as many times as you like. And then after the last time you met K, you went from K to J without passing things that are up to K because all the things were squished in here. Okay, let's enlarge this. Okay, we continue. So there was lots of discussion during the break about this proof here. So let me just reiterate once again, and you stare at this at home. That would be my advice. Things like this might occur in the midterm, and so midterm in this case. So RIJK, just one more time, is the words that start with I and in J. So they start you at state I, end you in state J, but all the states in between are less than or equal to K. So how can they be described? Let's look at the picture now. This is I, this is J. So either you start at I and you end in J without ever touching K, then all the states you're passing is from 1 to K minus 1. You cannot exceed K minus 1 if you're not even exceeding K. Right? So one way to go from I to J maybe is that you start at like this. So all the states are less than K minus 1. So this is one way. What is the other way? If you exclude this, the only things are left that pass through K. So now let's say I have one single road that goes from I to J and passes through K. How can this be decomposed? It can be decomposed like this. You start with I, you first hit K at some point, right? So you start with I, you hit K first. The fact that you hit K first means that all the states between were less than K minus 1, less or equal to K minus 1. So it's like this. Then, once you hit K, it might be that you hit K 7 more times. So you go from K to K like this, hitting it again and again and again, but again bounded by K minus 1. Because otherwise, this is how you decompose it exactly. So from K to K by K minus 1 like this. And then you have the last time you hit K, because you have to go from K to J at some point. And you go from K to J again, bounded by K minus 1, because it's the last time you hit K. K cannot happen anymore. So all your words decompose like this. So this is regular by induction. This is regular, this is regular, this is regular. Star is regular, concatenation is regular, everything here is regular. That means RIJK is regular, which we already talked, means that the language that your DFA accepts is regular. This concludes one side of the proof. Now let's discuss the other side of the proof. Let's not save this. There's a question, right? Oh. Okay, so now so what did I do, right? So let's discuss what we did. So we had the machine M, and we proved that LM is regular. Okay, so now what I'm aiming to do is the opposite. I want to start with a language and build M. So first I started with M and I proved that whatever it accepts is regular. Now what I want to do is I want to start with just a general regular language and I want to build the machine that accepts it. But now I'm doing something like this. Okay, my DFA is fairly simple, right? It has just finite states and I'm going around the arrows. It's very simple. What I'm going to do, what is the strategy now, is to make this, give it more freedom, make it more complicated. I'm going to introduce a new machine. So this is what I'm going to do now. This is my strategy. So I'm going to introduce a new machine called NFA. This is a shorthand for Nondeterministic Finite Automata, which actually is on the first look, it's improvement on DFA. Every DFA will be an NFA from the first look. We will prove that the converse is also true, but let's say we don't know this. I'm going to make M more complicated. That means it has more freedom. It can do more things. NFA on the first look can do more things than DFA. It will turn out that this is not the case, but on the first look, that's how it looks, that NFA can do more things. And this will make my job much easier because I have to build my machine. If I have more complicated machine at my disposal, of course it's easier to build. So I'm going to start with language L, and instead of building the DFA, let me write, so this is DFA, right? I have to build the deterministic finite automata. Instead, I will build an NFA, which is easier to build because it can do more things. So it's easier to build an NFA which accepts L because NFA does more things somehow. And then I will prove that NFAs and DFAs are the same. Meaning that whatever NFA accepts, so does the DFA. And that would mean that every regular language is also accepted by DFA. Is this strategy clear? So, okay, this is what we do now. So first we define non-deterministic finite automaton, and then if we get to, maybe tomorrow we'll get to pumping lemma. But what is an NFA? Non-determinism will hunt us throughout this semester. So we have to really understand what is the difference between non-determinism. So as I said, non-determinism will hunt us throughout this semester. What I meant, we are going to discuss non-deterministic Turing machines. We might discuss non-deterministic push-down automata, but I don't know if we have enough time for this. But for sure, we have to discuss non-deterministic Turing machines. And Turing machines are exactly the things that emulate modern computers. DFA is far too simplistic. You can code much more things than you can program in a DFA. Computer is somehow stronger than DFA. However, there is a thesis called Church thesis, but we'll cross that bridge when we get to it, that there is an abstract theoretical machine called a Turing machine that is exactly that should encompass everything that is computable, even in theory. And then we will have a non-deterministic Turing machine as well, somehow. And the famous problem P equals NP, the word N, P stands for polynomial, NP stands for non-deterministic polynomial, is exactly the same word that non-deterministic is here. So one of the, well, not one of the most famous problems in computer science includes the word non-deterministic in it. So let's try to understand what non-determinism is. As I was saying, this word means the same thing as it means for when you physicists talk about it. When you're rolling a dice, right, there's some randomness to it, what number turns out, but somehow when we say that the world might be or throw of the dice really is deterministic, what we mean that if I have the complete information, I know all the forces involved, I know the pressure, air pressure, I know air temperature, I know my mood, so I know every single atom, what the atom is doing and every single force involved, then when I throw the dice, in theory, I can exactly calculate how it will land if I know all the surface, how the surface works and everything. I exactly know the number the dice will land on. So it's deterministic somehow. Once I throw the dice and let it go, I can calculate what it lands on. So the information that I have here completely determines what is to come. It's the same thing with DFA, right? If you're standing in a state and the letter is coming in, your input is coming in, it's 0 and 1, you're completely determined where you're going to go next. So if it's state Z0, let's say, and 0 is coming in, you know from your transition function that you have to go to state Z1. In non-deterministic automaton, you will have a choice somehow. So when some input comes in, there's many different things that your machine can do. So should we dive into a definition first, or should we really actually give an intuition? Let's give an intuition. So the non-deterministic automata will be something like this. So in DFA, you have this, let's say you have state like this, let's say Z5, I don't know. So the state, whatever, so it's maybe a start state, whatever. And then let's say your alphabet is again just B, so 0 and 1. So let's say with 0 you go here, with 1 you go here. So Z17 and Z4. So this is a DFA. Well, this is just a part of a snapshot of a DFA, but let's imagine, so when 0 comes in, you know to go to Z4. When 1 comes in, you go to Z17. What NFA will do is somehow you will have a choice. So when 1 comes in, you can also go here. This will be an NFA. So it's non-deterministic. It's not completely determined that if you're starting at Z5 and 1 comes in, you go to Z17 or Z12. So there are two possible options. This is all there is, but somehow we'll add more things to it. But how do I describe it as mathematically? So remember what DFA was basically. DFA basically what? So you had this. So you had this function delta that goes from ZA to Z, right? What this means is if you give me one state and one letter, I produce another state. This is no longer true in NFA, because if you give me a state, that is the state I'm standing at, and you give me letter, let's say 1, I cannot produce just one state. I do not want to produce one state, basically. So let's say DFA would say that delta Z5, 1 is equal to Z17. That means that if in state Z5 I read 1, I have to go to Z17. What NFA in contrast would say is that when I read the state, so Z5, and I read 1, either I can go to Z17 or what was it, Z12. So this can be two things, Z17 and Z12. This is all there is. Can you guys actually mathematically say what delta should be then? So let's say delta Z A, where should this go? State times გაერთიანება Z-ია. So subset-ებში რა. So it should be so all possible subsets of Z. So sometimes they write 2 to the power Z. What is this? This is just a notation that means all possible subsets of Z. So this includes even empty thing. It includes the whole Z. It includes all singletons like Z7 and so on. It also includes, I have to scroll down. It also includes like double things. So like, what the hell? Like Z12, Z17. It also includes triples, like 3 states, and so on. But it's still finite. How many elements are in all possible subsets of Z? 2 to the power Z. This is why this is the notation. It doesn't mean a number, it means 2 to the power Z, but how many elements are there? Exactly this many elements. However many elements are in Z, 2 to the power Z is how many subsets you have. And now what the machine does now, for every state and every letter, it gives me a subset. For example, if it gives me this subset, it means that when I'm in the state and I read this letter, I can go to Z12 or Z17. როგორც გინდა. არა, ნახე. დიდი ამაში დავთო. Ah, let's actually do this. So the question is, why is there power of 2 subsets? Why is there power of, so let's say Z, god damn it, I cannot write. So Z is some set here. Let's say, let's name them with natural numbers just for simplicity. 1, 2, 3, up to n. So it's some finite subset. I just named them 1 to n. How many subsets does this have? Yeah, why is it 2 to the power n? This is the question, right? Now, what is the subset here? The subset here is I have to pick which things are in the subset and which things are not. For example, here, I picked a subset 2, 3, n. So each element either is in the subset or not in the subset, right? So each subset now corresponds exactly to a string that contains like 0, 1, 1, 0, 0, 0, 1. See what I'm saying? So every time you pick a subset, you specify a string of ones and zeros. Ones, you write ones where you take the thing that included in, for example, if you say 1, 1, 1, 1, 1, 1, it's the whole thing. If you say 0, 0, 0, 0, it's the empty set. So how many strings are there? 2 to the power n, because there are 2 possibilities here, 2 here, 2 here, and so on. So the 2 to the power n ways. So for every element you say yes or no in the subset. So there's 2 to the power n ways to say yes or no. And that's why there's 2 to the power strings. And hence this notation here. This notation just means all possible subsets, but they also write 2 to the power z because this is as many subsets as there are. But anyway, so this is the official definition that we also came to from our discussion. The official definition of, so let's enlarge this. So what is the official definition of an NFA, non-deterministic finite automata? It's the same exact thing. I have finite tape, so this is an input tape, my alphabet. I have finite set of states. However, the only difference is that my delta is now set valued. For every z and every a, I get a set. Again, I have an initial state and I have sum of accepting states. Okay? And the idea is that if an automaton is in state S and reads input A, then where does it go? Then delta, so if it's in state S and reads A, delta SA is now a set. It's not a single thing. So it can go to S prime if S prime is in here. So this might contain 5 different states, and it can go to each one of those states. So instead of equality, I have now inside. So it's inclusion. This is all that changed. Before this was a unique thing. Now it has many things. So it can go to state S prime. Okay. So what? You have seen this, it turns out, in hardware lab and OS support, in MIPS plus disk ISA, and I2OS C0 plus disk. So you have seen NFAs. But this gives us tremendous power. Look. I have not said what accept means, but we will into it. What is this DFA here? This is your start state and also the accepting state. It only reads ones, and it has 7 ones this way and 25 ones this way. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, up to 25. Now this is not a DFA because if you start here, when you read 1, where do you go? Do you go here or do you go here? It's not a DFA. So you cannot do this in DFA. But in NFA, you can either go here or go here. And now what I'm going to say is that your NFA says accepts the string. This is the important definition. It says yes on the string if there exists at least one way to the accepted state. So to continue, so I will say that the string is accepted if there exists a path that goes to an accepting state. So in this case, the string 7 ones will be accepted. Why? Because I will go this way. 1, 2, 3, 4, 5, 6, 7 and accept it. If I go this way, to begin with, it will not be an accepting computation because it will go like 1, 2, 3, 4, 5, 6, and it will get stuck somewhere here, right? And it's not an accepting, but since there exists another road that takes me to an accepting state, and I say it accepts 7 ones. It also accepts 25 ones. I'm claiming that it also accepts 32 ones. Do you see why? Why does this NFA accept 32 ones? Yeah, first you go down and then you go up. So it do you know what language this thing accepts? Zustad romelerteps ramdenerteps ireps. Does this accept 14 ones? Yes. It accepts 32 ones, 14 ones. Does this accept 50 ones? Yes, you go down twice. Yes. Does this accept 57 ones? Yeah, you go down twice and 1 up. So it exactly accepts the language that we had before. 1 to the power 7i plus 25j. So remember, it was hard to think of a DFA that accepts that language, but it's very easy to create an NFA that accepts that regular language.
Well, I have a question. Can't we construct a DFA with 25 states, and we have the set of accepting states that are exactly usages of 7 and 25?
I don't know exactly if that is the truth, but you can always, we will prove that if you can build an NFA, you can always build a DFA. That is the idea. That is the whole point, that even though NFA looks more powerful because it's very easy to build, for example, here, and maybe you need some kind of GCD and some other constructions for DFA, we will prove that these two things are basically the same. Okay, but now let's define what a configuration is, by the way. We have to get used to these things here. What is a configuration? So remember what was configuration for DFA? The configuration was something like this. So you have a state and letters, W1 to Wn. So your DFA is in state Z, and it's reading the word from W1 to Wn. And what did we say that the next configuration was? In case of DFA, we said that if you have configuration state and words, and then the other configuration different state and one less letter here, so it starts with W2, then we said that K prime was next configuration of K if Z prime was equal to delta ZW1. I think some of you said this. So what is the next configuration of this one, right? So for NFA, in contrast to DFA, Z prime has to be this is a set. It contains many different possibilities where you can go when you read W1, and Z prime is one of those possibilities. And now there are many different computations. This is the non-deterministic part. If you're in a configuration K in a DFA, there's a unique next configuration. But in this case, there are many different next configurations, all with different states here. And all these different states will be different members of this set. So now your configuration is not like this unique guy that follows down this tree, if you think about it. It's like many different ways, and your tree has as many nodes as there are sets as there are elements in delta Z W1. But so this is successor configuration. I think it's clear what we mean here. So what next? Okay, again, what is a computation? Computation is a sequence of these things where each one is the next possible configuration. You start with the start state and the whole word, and you have to end somewhere with the whole word read. And I will say that the computation is accepting if Z prime is an accepting state, and I will say that M accepts W. This is what we said before, and I will just mathematically state it that let's enlarge this, that your machine accepts W if there exists an accepting computation. There might be many, there might be some that are not accepting, but if there exists at least one accepting computation, so one road you can follow to an accepting state, then I will say that this W is accepted. And again, by LM, I will denote all words that are accepted, but in this case now, by NFA. So this is just what we said, but now I made it more, whoa, what's happening? And yeah, as we said, this actually, for example, accepts 1 to the power 14, but it rejects 1 to the power 5. Why? Because there's no way I can go 5 steps that I'm gonna get accepted. Maybe even 11. Does 1 to the power 11 accepted? No, because any way I go here or here, I will end up here, I will end up 7 and somewhere here. And if I go here, I will also end up somewhere in this state. So 1 to the power 11 is not accepted here. There is no accepting computation. However, 1 to the power 57 is accepted because I go twice low down here and 1 time up here. So we see that NFA is more powerful. And now we come to, we might actually prove this. Now we come to this thing here. For every NFA M, there exists a DFA M prime which accepts the same language. So what I'm saying that if you built me an NFA, you can also build me a DFA. Now, why do I want this? So let me go back to the first strategy I said. I'm going to start with a regular language. I'm going to build an NFA that accepts it. A very easy NFA that accepts it. And I will know from this construction that, okay, DFA also exists. I'm not going to build a DFA. I can, but it's easier to build an NFA. And using this lemma here, I know that I can build a DFA. And then I will prove that DFA and regular languages are the same. Also, NFA and regular languages are the same. Okay, so let's prove this, but let's actually guess the proof first. Let's guess what the proof should be. Let's start with actually an easy example. So let's look at that language that we had before, but instead of 7 and 25, let's take something easier. Let's take 2 and 3. 2 to the power I plus 3 to the power j. So let's take this language. Maybe like this. So I, j are natural numbers. Can you tell me what this language is? What does not, so let me ask you to simplify your life. What is the string that this thing does not contain? Oh yeah, this also includes 0, by the way, yeah, I forgot. Ertsals ու ertsers. Როგორ დაწers აბა ertsals? Huh? How can I write just single one? Როგორ? No sakur that's. So it is everything. So it's like 1 star somehow. It's everything minus just this guy. So it can write everything other than this. Now, I must say because so every even number can be written by this guy. Every multiple of 3 can be written by this guy. And so every multiple of 5 you can get this way. And the only guy left is just 1. Somehow this is. But anyway, so we do not care about to prove that this is the case. Intuitively, this is the case. Because these two things are prime, whatever. But what I'm going to build now is I'm going to build an NFA of this very easily that accepts this. So let me write the same, in the same exact vein as we had before. This is an accepting state. Then I will have 1, 2. And then I have 1, 2, 3. This is an NFA that accepts this trivially, right? Because if I want to build, I don't know, 1, 2 to the power times 7 plus 3, damn it, 3 times, I don't know, 5, what do I have to do? I go 7 times here, 5 times here. It exactly translates, right? Once you give me I and j, I have to go I times here and j times here, and I will end up here, right? But of course, the only thing this NFA does not accept is just single 1, because either I go here and I'm stuck, or I go here and I'm stuck. Everything else is accepted, because 2, for example, accepted here, and so on. Okay. Now let's give this guy's names. So let's call this guy, I don't know, let's call this guy Z0. Let's call this guy, I don't know, Z1. Let's call this guy Z2. And let's call this guy Z3. And now I'm going to build a DFA for you. So in this case, I just took my alphabet is just 1. Doesn't equal 0. This is just for simplicity, but you can do it in general, like complete generality. But how would I go about building a DFA from this? I would start with my start state, again Z0. But I will put funny things around it just for the show. So I start here again. Now I'm building a DFA. And I will take the same alphabet. And now the 1 is coming in. Where am I supposed to go? I'm reading it here, so either I go to Z1 or Z2. What I'm going to do is I'm going to create a state here, which I will call Z1, Z2. See what I did? Okay. Then what? Then let's say 1 is coming in. Where am I supposed to go here? So this is Z1 and Z2. What I'm going to do is I'm going to look at Z1 and Z2 here. You should probably at some point get that this is the right thing to do. When I read 1 at Z1, I go to Z0. So I'm going to write Z0. Again, with things here. And when I read 1 at Z2, I go to Z3. See what I'm doing? I'm looking at my DFA here, and I'm looking where the things go, and I'm writing both of them. Yeah, but but this is not the same. This is state called Z0. This is state called Z0, Z3. This is not the same. It is just... Huh? It doesn't, it's just a name. Imagine there is nothing written here. Imagine you don't see anything. So then the name is 1, 2, and 3 of the state. Yeah, the reason why I'm naming it this way is so that you see how I build this from this guy. So from Z0, Z3, where does this thing go? I look where does Z0 go with 1. Z0 with 1 goes to Z1 and Z2. So it goes to Z1, Z2. This is where Z0 takes me. Where does this 3 takes me? Z3 takes me to Z0. So it's the state named like Z1, Z2, Z0. And then everything goes back here. Why? Because Z1, it's everything. So I can look here. Z1 goes to Z0, Z0 goes to Z2, Z2 goes to Z3, Z3 goes to Z0. Oh yeah, it's not everything, right? I'm missing something. Z3 went to Z0. Yeah, Z1, let's look. Z1 goes to Z0. So let's not write this. I thought I had only 3 states. I have 4. So this goes like this, if I'm not mistaken somewhere. Where does Z1 go? Z1 goes to Z0. Where does Z2 go? Z2 goes to Z3. Where does Z0 go? Z0 goes to Z1 and Z2. So it's Z1 and Z2. So it's like this. Now this is everything. If I do it one more time, I will end up back here. So this is now a DFA. I can actually imagine you do not see this. You do not see this at all. Okay, I have to say, what is the accepting states now? Oh yeah, why did I mark accepting states here in the beginning? I didn't know this. I know that this is a start state, but which ones are the accepting states now? Accepting state ikneba isini. So let's take the ones that include accepting states here. So Z0 is the only accepting state here. So I will mark this as an accepting state. And I will also look where is Z0. Oh, here. This is also accepting. Oh, here. This is also accepting. Wherever I see an accepting state, I make it an accepting state also. Wherever I see Z0, I made it accepting. So this is now a DFA. Look, I can just call it state 1, state 2, state 3. Don't care about the name, state 4. It has 5 states, and these are my transition functions. Okay, look at this DFA now. What language does this accept? So, only language that is not accepted is this one here.
We're discussing what language a determinist.
So this one here, right? Everything else is accepted. Exactly this language. This is how you build a DFA from the NFA. What I did basically here, conceptually, what I did is I looked at my NFA and I looked at all possible ways it can go from a single point. So it might go this way, and I collected all of them in one state. This is all I did. Then again, I looked at all possible ways it can go from there, and again, collected in one state. And I can create unique states this way, and it somehow collapses all the possible ways into a one way. So I started at Z0. There are 2 ways to go, so I collapsed them into one state. So I just glue the different states together. You can think of it this way, that I glued these 2 things together, and then again glued things together following the arrows. And this is basically what is done here, by the way. Let's go through the proof that actually does the same exact thing. So what you do is you start with a non-deterministic automaton M, and you want to build M prime, which accepts the same exact language. How do you build this? How do I build this? What are the states? I would just say, states are all possible subsets again. By the way, yeah, I'm overshooting here. Look. Here I have states are what? Z0, Z1, Z0. These are just names. These mean nothing. Z0, Z1, Z2, Z0, Z3, Z1, Z2, Z whatever. But there's also, what about the state, let's say, I don't know, which one is missing here? I don't know, Z1, Z2. Z1, Z2 is here. Z1, Z3 is not there. What about this state? This does not occur here, but it's still a subset. I can still have the state somehow, but it's never reachable if you start here. If you start here and only follow the things you can follow, you will never hit the state. For example, I can do the same game and draw what happens when I input 1 here. From Z1, where do I go? I look at my NFA. From Z1, I go to Z0. And where do I go from Z3? This 3, I go to Z0 again. So it's like this. So basically this state actually connects here. It's like this. So let me erase this. But somehow this state can never be reached if you start here. So I didn't even draw this. So what is done here, let me pause the recording and explain this in Georgian. This is all that's happening here. So all possible states are all possible states. Again, the start state, let me enlarge this. The start state is the same state, Z0, but with the curly braces I wrote. And this is the most important part. Let's say I have a subset, that means Z0, Z1 state. The name of the state is 0, 0, Z1. And I read my letter A. Where do I go? I go to all possible states. If I look at all possible states in Y and all possible ways my NFA was going from Z to A, and I collect them together in a union. Exactly the thing we were doing when I described when you go from Z0 to two things and collect them together is exactly what is happening here. You look at all possible states in Z, look at where do these things go, and you collect them together. And what is an accepting state? Accepting states are exactly those states that have accepting states in them. In mathematical, this means if you take an intersection of your Y and accepting state, it's not empty. So if the name of your state contains an accepting state, in our example this was Z0, then I will call it an accepting state. So here in our example, this was this guy, this guy, this guy, and this guy. Everything that contains Z0. This is the whole construction, but then one has to prove that this works. How do we prove that this thing works? Let's see if we have enough. We have 1 minute, so we will prove it next time how this thing actually looks tomorrow. But I highly advise you to look and understand this definition. If you do not understand, you have to understand what NFA is. And if you do not understand what NFA is, then this proof will go over your head. Yeah, might as well.